Hello AP Stats, this is Mr. Moon. I'm recording this video for 4.2b slides so that those of you that are on the Macbeth trip today can catch back up. So today we're talking about how to experiment well, and what we really want to look at is a comparative experiment that includes random assignment. So last time we talked a little bit about confounding and how we sometimes get into scenarios where our treatment changes more explanatory variables at once than we want. So one remedy for this is to perform a comparative experiment where some units or subjects receive one treatment and similar units receive another. Most well-designed experiments are going to compare two or more treatments. So comparison alone isn't enough. If the treatments are given to groups that differ greatly, we're still going to have bias. So, for example, if we had all the highest performing math students go in one group and all the lowest performing math students go in another group, and we test them on any kind of academic thing, as you might expect, we'd get some bias between those two treatments. So the solution to this problem of bias is random assignment. In an experiment, random assignment means that experimental units or subjects are going to be assigned to treatments at random, that is, using some kind of chance process. The subjects are definitely not choosing the group that they get to be in. So the experimenter is doing that with some sort of random assignment. Okay, so first we want to talk about completely randomized design. And this is where the treatments are assigned to all the experimental units completely by chance. So basically, if you walk into this study, you have a 50-50 chance of being in treatment 1 or treatment 2. Some experiments may include a control group, and a lot of well-designed experiments do include this control group. And this control group is going to receive either an inactive treatment or an existing baseline. So usually this is some kind of, like, let's give them the non-effectual treatment to compare the new treatment that we're trying out. Okay. So to look at what this looks like, here's our experimental units or subjects coming into the study. We use random assignment to break them into group 1 and group 2. Group 1 gets treatment 1, group 2 gets treatment 2, and then we compare the results. Okay, let's talk about 3 principles of experimental design. So the goal here for a randomized comparative experiment is it's supposed to give good evidence that the differences in the treatments actually cause the differences we see in the response. Remember that one of the major reasons we do experiments is to see causality. So to pull this off, we need to follow some principles of experimental design. The first one is going to be control. We want to control for any lurking variables that might affect the response. And the way we can do this is use a comparative design. So have your 2 similar treatment groups going through the 2 different treatments and then compare the results. And then you're ensuring that the only systematic difference between the groups is the treatment administered. Secondly, you want to use random assignment. You want to use impersonal chance to assign experimental group units to treatments. So this is going to help create roughly equivalent groups of experimental units by balancing the effects of lurking variables that aren't controlled on the treatment groups. So you definitely don't want to let your participants self-select into one group or the other, because this is going to tend to lead to bias. You're going to get generally a lopsided grouping with a lot of, if you have, say, one friend group who are very similar on some aspect, all go into one group. Okay, now you have a problem because that group now is different than the other in some kind of key way. And finally, replication. You want to use enough experimental units in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. So if we have one subject in each group, that's probably not enough. We may just have, somebody who leans a particular way, opinion-wise or athletic-wise or academic-wise, whatever we're studying, in one group and someone who's very different in the other. If we have a couple of subjects in each group, generally we try for a higher sample size, then that's usually going to flush out any of those differences as we include more and more subjects. So the key here, we want control. We want to make sure there are very few differences between the groups except for the treatment administered. Random assignment, we want the assignment to each group to be by chance, and we want to make sure there's replication. So we want enough subjects in each group that we're not going to see, one outlier swaying the results. As an example, I'm going to give you guys the physician's health study on page 241. And you guys can see here what we have this is actually a two-factor study. So we wind up with 4 treatment groups. One group gets aspirin and beta-carotene. Another group gets aspirin and a placebo. A third group gets placebo and beta-carotene. And the fourth group gets a placebo and a placebo. So I want you guys to think about how this experiment follows all the principles of experimental design that we just talked about. Think about control, think about random assignment, and think about replication. You may need to actually open up the study on page 241 to see some of the details. But think about how this experiment does follow those. And also I want you to carefully look at this chart and see for the control dimension how similar each of those groups is to the one next to it. You should notice that they only differ from each other in one way as we move from box to box. Okay, that's all for today. We're going to pick up with 4.2c, which I think talks about experiments and what can go wrong, and really how to design a good experiment with a couple more tips. So I will see you guys in class then, and for now, that's all for me. Have a nice night.